In this video, we're going to work on two more exercise questions. So exercise question 3 and 4. So if you already feel very comfortable with exercise question 2, then exercise 3 and 4 are pretty much repetitive. So you can just try on your own first, then maybe watch a video and to compare your solution with my solution. Look at question, let's start with exercise question 3. Customer in arrival time follow exponential distribution. The average in arrival time is 2 minutes. So read the question, we know the average in arrival time is 2 minutes. What is that? What is average in arrival time? Which is that something we just discussed in the very beginning of this class, which is A, which is average in arrival time is A. So look at question 3.1. What is the arrival rate per minute? Okay, arrival rate. So basically the question asking about lambda per minute, lambda. So the question itself doesn't tell us what is lambda. The question only tells us what is A. A is 2 minutes. So we know A and lambda are interchangeable. So basically if we know the value for A, we can also calculate the value for lambda. So A is 2 minutes, as A and lambda are interchangeable, then we do the formula lambda equal to 1 over A is 1 over 2, it's 0.5 per minute. So the arrival rate is 0.5 customer per minute. Next question, question 3.2. What is the probability that the next customer will arrive in 3 minutes? So talking about probability, we only have two possible distributions, either exponential distribution or Poisson distribution. So question 3.2 talking about when the next customer will arrive in 3 minutes. Next customer arriving in 3 minutes basically means the in arrival time between this customer and next customer will be less than 3 minutes. So obviously we can use exponential distribution. So this question is about the time between two customers, so we can use exponential distribution. So lambda is 0.5 per minute from question 3.1, and t is 3 minutes. So t is 3 minutes. In 3 minutes, so t is 3 minutes. So you can see 0.5 per minute and 3 minutes are consistent. We can use the formula. So this is talking about in arrival time less than 3 minutes. So we can use this formula. So 1 minus the exponential function. So we plug in the right value for lambda and t, we'll get the number 0.7769. So in other words, there's a roughly 77% chance the next customer will arrive in 3 minutes. Next question 3.3. What is the probability that the next customer will arrive in 1 hour? Next customer arriving in 1 hour, this is talking about what? Talking about in arrival time. The in arrival time between this customer and next customer will be less than 1 hour. So we can use exponential distribution. However, please pay attention to that time unit. So here we're talking about 1 hour. Okay, 1 hour. So we have to use per hour arrival rate, or we have to convert 1 hour to minutes. So the question is about the time between two customers, so we can use exponential distribution. So lambda is 0.5 per minute, but here we have 1 hour. 0.5 per minute is not good. So we have to convert 0.5 per minute to how many per hour. So 0.5 per minute means you will see average-wise, you will see half customer per minute. That's equivalent about 30 customer per hour. So 30 customer per hour, 1 hour, these two numbers are consistent. Now we can apply the formula. So this is the formula. We plug in the right value for both lambda and t, which is 30 and 1, we'll get a number close to 1. So when you do this number, this term, this exponential function, you will get a number really, really, really small. So basically you can ignore it. That's all, get 1.0. It's 100% chance, almost close to 100% chance the next customer will arrive in 1 hour. Now let's move to question 3.4. What is the probability that there are no customer arrival in the next 2 minutes? No customer arrival in the next 2 minutes. As we discussed in exercise question 2, this is special case. Okay, this is special case. So when we see no customer arrival in a period. This is special case. For this special case, we can apply both exponential distribution or Poisson distribution. So first of all, no customer arrival in 2 minutes. No customer arrival in 2 minutes is same as the inner arrival time is more than 2 minutes. So inner arrival time between this customer and the next customer is more than 2 minutes. That's equivalent as saying there's no customer arrive in the next 2 minutes, okay? Because the next customer will arrive after 2 minutes. So we can view the question as time between two customers, so we can use exponential distribution. So lambda is 0.5 per minute, t is next 2 minutes, so t is 2 minutes. So by applying the corresponding formula, here be careful, here we're talking about the inner arrival time is more than 2 minutes, not less than 2 minutes. So this is the right formula. So exponential function, negative lambda t, so plug in lambda, plug in t, we get 0.3679. So there is about 36% probability that there are no customer arrival in the next 2 minutes. So this is how we do it by applying exponential distribution. And also we can view the question as a number of customers in a period. Here you can see there are no customer in 2 minutes, or in other words, 0 customer in 2 minutes. That's why we can apply the Poisson distribution. So to apply the Poisson distribution, we use this formula. So we need 3 pieces of information. One is n. N is the number of customers. So in this case, n is 0 customers. So n is 0. We also need a lambda. Lambda is 0.5 per minute. And t is 2 minutes. So we plug in all the numbers, we'll get the numbers 0.3679. So you can see they are basically the same. So these two numbers are the same. Because regardless which distribution you use, the final solution should be the same. So you exponential distribution versus Poisson, the final answer is the same. So now we go to question 3.5 and question 3.6. So question 3.5, what is the likelihood that there is exactly 1 customer arrival in the next 2 minutes? So 1 customer arrival in 2 minutes. So 1 customer in 2 minutes, it sounds like Poisson distribution is the right distribution to use. So how many customers in how much time? So the question is about the number of customers in a period, so we can use a Poisson distribution. So lambda is 0.5 per minute, t is 2 minutes, n is 1, so 1 customer in 2 minutes, so n is 1. So we apply the formula, and plug in all 3 numbers, we get 0.3679. The last question for exercise problem 3 is question 3.6. What is the probability that there are exactly 2 customer arrival in the next 2 minutes? So 2 customer in 2 minutes. So how many customer in a period? So again, we can use a Poisson distribution. So we need 3 pieces of information. Lambda is 0.5 per minute. Arrival rate, t is the time, 2 minutes, and n is 2. So the question is talking about 2 customers in 2 minutes. So n is 2. So apply the formula. So plugging all these numbers, you do the math, you get 0.1839. So feel free to pause the video anytime you want, so you can try the question on your own first, then you can look at my solution. So the last question is basically talking about there is a 18% probability that you might see 2 customers in a 2-minute time window. Now let's move to the last exercise question. So exercise question 4 is very similar to 2 and 3. It's just different numbers. So if you already feel very comfortable with exercise question 2 and 3, you may ignore it. Depends on how much time you have. So let's read the question. Customer inner arrival time follow exponential distribution. The average inner arrival time is 4 minutes. So what is that? Average inner arrival time, 4 minutes. That means A is equal to 4 minutes. Okay. But in general, regardless of which distribution we use, either Poisson distribution or exponential distribution, we need the value for lambda. So A is not sufficient. We need to convert to lambda anyway. So let's look at question 4.1. What is the arrival rate? The arrival rate per minute. Arrival rate per minute, talking about lambda, but it's a per minute lambda. So we know A is equal to 4 minutes. That's from the question. Average in arrival time 4 minutes. So A is 4 minutes. As A and lambda are interchangeable, so we want to go from A to lambda. So lambda is equal to 1 over A, so 1 over 4. So you get 0.25 per minute. So that is the arrival rate per minute. Question 4.2. What is the probability that the next customer will arrive in 4 minutes? Next customer arrive in 4 minutes. In other words, what is the probability that the in arrival time between this customer and the next customer is less than 4 minutes? So obviously we can apply exponential distribution. The question is about the time between two customers, so we apply exponential distribution. So lambda is 0.25 per minute, and t is 4 minutes. Again, for consistency, basically these two numbers are consistent, 4 minutes versus 0.25 per minute. No need to convert anything. Then we apply the formula. Now here, we're asking about probability that the in arrival time is less than 4 minutes. So this is the right formula. Remember, there are two formulas for exponential distribution. One is asking about the in arrival time is less than something. The other one is asking about the in arrival time greater than something. So here is less than something, we use this formula. So 1 minus exponential distribution, lambda t, we'll plug in the right number, we get 0.6321. So there's about 63% chance the next customer will arrive in 4 minutes. Question 4.3, what is the probability that the next customer will arrive in half an hour? In half an hour. Next customer arrive in half an hour. In other words, how likely the in arrival time between this customer and the next customer will be less than half an hour. So this sounds like the right case to use exponential distribution, the in arrival time. The question is about the time between two customers, so we can use exponential distribution. So lambda is 0.25 per minute, or equivalently 15 per hour. So 0.25 per minute times 60 minutes, you'll get 15 per hour. So why do we convert? The question is, we already know the lambda is 0.25 per minute. Why do you want to convert to 15 per hour? Because here, t is half an hour, it's 0.5 hours. So for consistency reasons, we have to make sure lambda and t have to be consistent. So t is half an hour, 0.5 hour. We want to convert lambda to the arrival rate per hour. So it's equal to 15 per hour. So how do you go from 0.25 to 15? Simply times 60. Then we can apply the formula. Again, this is talking about in arrival time less than something. So we use this formula. So plug in the right value for lambda t, 15 and 0.5. You do the number, you get 0.99945. There's a 9.99945 probability that next customer will arrive in half an hour. Now let's look at question 4.4. What is the probability that there are no customer arrival in the next 2 minutes? Again, we see no customer in 2 minutes. No customer in 2 minutes. That means we might be able to apply those distribution to figure out the solution. So no customer arrive in 2 minutes. Here we're talking about no customer. If we see one customer, two customers, then the only distribution that applies are Poisson distribution. You can no longer use exponential distribution. But if you see no customer in 2 minutes, you can use exponential distribution as well. So no customer arrive in 2 minutes. That means what? No customer arrive in 2 minutes. That means the in arrival time is more than 2 minutes. So we can view the question as a time between two customers. So we can apply exponential distribution. So in this question, lambda is equal to 0.25 per minute. T is at 2 minutes, in the next 2 minutes. So by applying the corresponding formula, so this question we're talking about the in arrival time is greater than 2 minutes. So that's why we use this formula. Remember, there are two formulas for exponential distribution. So when it's greater than 2 minutes, greater than something, we use this formula. So we plug in that right value for both lambda and t, we get a number 0.6065. So there's about 60% chance you may not see any customer in the next 2 minutes. And also we can use view the question as a number of customers in a period and apply Poisson distribution. Here, basically the question is talking about the probability that you will see 0 customer in 2 minutes. So 0 customer in 2 minutes, we can use Poisson distribution. So this is a formula for Poisson distribution. But for Poisson distribution, we need 3 numbers or 3 pieces of information. So first of all, we need a 0. We need an n. N is a number of customers, which is 0. Then we also need a lambda and t. Lambda is 0.25. T is at 2 minutes. So we're plugging all the values. We'll do the calculation. We get 0.6065. So you can see these 2 numbers are consistent. Again, they are consistent. They should. They have to, because solution should be the same regardless how you approach the question. So 2 more. Question 4.5, question 4.6. So first of all, let's look at question 4.5. What is the probability that there is exactly 1 customer arrival in next 2 minutes? So 1 customer arrival in 2 minutes. As I said, only if you see no customer arrival in 2 minutes, you can apply both distributions. Here, we're talking about 1 customer arrival in 2 minutes. The only distribution you can apply is that Poisson distribution. So 1 customer in 2 minutes, Poisson distribution. So the question is about the number of customers in a period, so we can use Poisson distribution. So lambda is at 0.25 per minute. T is 2 minutes, next 2 minutes, T is 2 minutes. N is how many customers? Exactly 1 customers. So N is equal to 1. So use the formula. We're plugging all the values. We do the calculation. We get 0.3033. So there's about 30% chance you might see exactly 1 customer in the next 2 minutes. The last question, question 4.6. What is the probability that there are exactly 2 customer arrivals in the next 2 minutes? Again, 2 customer in 2 minutes. You can use a Poisson distribution. How many customer in a period? So this is a Poisson distribution. We cannot use exponential distribution. Okay, only if there's 0 customer, you can use exponential distribution as well. So the only way we can approach the question is using Poisson distribution. So the question is about the number of customers in a period, so we can use Poisson distribution. So we need 3 pieces of information. Lambda is 0.25 per minute. T is 2 minutes, next 2 minutes. N is 2 customers. So we use a formula, plug in the 3 numbers, we'll get number 0.0758. In other words, there's a little over 7% chance you will be able to observe exactly 2 customers in the next 2 minutes. So that concludes the online session for chapter 12.